Hey guys, so as promised, here is where matrix algebra gets a little bit tricky, but we're going to make sure that we do not lose our way because we are going to follow directions very explicitly and intentionally. And I recommend that you take notes in order to get through this because it is confusing, and I promise you, you will get lost if you don't write down exactly the process here that we're following when we multiply matrices together. Okay, the first thing, so I've got a matrix over here on the left and I've got another one on the right, and I would like to multiply them. Okay, now before any multiplication of matrices can happen, we need to make sure that the multiplication is defined. So in order to do that, we need to first determine the dimensions of each matrix, okay? So remember, it goes in rows by columns. That's how you determine a dimension of a matrix. So in the matrix on the left, I have 2 rows, right? So 2 by, and then I have 2 columns. So that matrix is a 2 by 2. That's rows by columns, okay? And then the matrix on the right, I also have 2 rows and 2 columns, okay? So rows by columns. The way you determine if multiplication is defined is if these 2 numbers right here are exactly the same. If those 2 numbers there, the column number from the one matrix and the row number from the other matrix, those 2 numbers there have to be the same. If those 2 numbers are the same, the multiplication is defined, okay? And the product matrix that you will get will have the dimensions of the other 2 numbers, okay? So from this little characterization here of our dimensions, we know that the column and the row are both number 2, so multiplication is defined. When we multiply, our solution matrix is going to be a 2 by 2, okay? So what we are going to do is write down our solution matrix, which will be a 2 by 2 as well. Okay, now, here comes the interesting stuff, okay? Now, if we want to fill in that first entry in our matrix, the upper left, that upper left is in row 1, column 1. So we're going to go to the first matrix on the left, and we will use the entries from row 1. Then in the other matrix, we'll use the entries from column 1. Again, that's because that entry right there in the solution matrix is in row 1, column 1. Okay, so here is the way that multiplying matrices works, so to speak, okay? All right, so we're going to start with row 1, and we're going to multiply A times E, and to that we are going to add B times G. Okay, so A times E plus B times G. Okay, now what we're going to do is we're just going to move through these one at a time. Okay, so now let's say we want a number to go in row 1 column 2. Okay? The first matrix, we use row 1. The second matrix, the one on the right, we're going to go to column 2. And that's because the entry that we're looking to fill in our solution is in row 1, column 2. So we'll start with A, and we'll multiply by F, plus B times H. Okay? And we will continue this. So obviously, so let's do second row there, first column in our solution matrix. Second row, so the second row in the matrix on the left, first column, so column 1 in the matrix on the right. So obviously, if you have not yet figured out what's going on, this first entry in the row is multiplied by the first entry in the column. So C times E. And then to that, we will add the second entry in the row times the second entry in the column. So D times G. Okay? And then if we're doing the last opening in our solution matrix is row 2, column 2, okay? We'll look to row 2 from the matrix on the left, okay? We'll look to row 2 over here, and then column 2 over here, which is going to give us the solution in row 2, column 2 solution matrix, okay? So the first entry in the row times the first entry in the column plus the second entry in that row times the second entry in that column, okay? And that is the pattern that you'll follow in order to perform multiplication of matrices. So let's actually put this in action. Okay, so we have matrix A over here. Okay, so let's keep the numbers very small. 1, 2, 3, and 1. And then matrix B. Okay, we'll do 2, 4, 1, and 5. Okay, so we need to see, is it possible to multiply A times B? Okay, can we do that? If so, we need to perform the multiplication. Before we do that, we first need to determine if whether or not we are allowed to do A times B from finding our dimensions, okay? So the matrix A is a 2 by 2, 2 rows, 2 columns, and matrix B is also a 2 by 2. So we know, because these two numbers are the same, that the multiplication is defined, and then we also know that the solution matrix is also going to be a 2 by 2. 2 rows, 2 columns. Okay, so we can multiply A times B. So the first spot that we'll fill is row 1, column 1. So we'll work in row 1 from matrix A and column 1 from matrix B. The first entry in A times that first column entry in B plus the second column, or the first row, the second entry in row 1 from A times the second entry from column 1 in B. So 1 times 2 is 2 plus 2. That means that the solution in row 1, column 1 is a 4. Okay, so let's just keep going straight across our row. We'll go from row 1 to column 2, which is going to give us this entry right here. Okay, so row 1, column 2, the first entry in row 1 is 1, the first entry in column 2 is 4, plus the second entry in row 1 is 2, the second entry in column 2 is 5. So 4 plus 10 is 14. Now let's move on to that position in our matrix, which is row 2, column 1. So we'll go to row 2, column 1, and do the same thing. The first entry in row 2 times the first entry in column 1 plus the second entry in row 2 times the second entry in column 1. So that's 6 plus 1, and we get a 7. Okay? And then finally, we are looking to fill in row 2, column 2 in our solution matrix. So row 2, column 2, the first number in row 2 multiplied by the first number in column 2, the second number in row 2 times the second number in column 2. So that's 12 plus 5 is 17. Okay? Now there may be instances in which our multiplication might be defined, say multiplying A times B, but it would not be defined if you multiply it the other way, like B times A. So for example, let's do A. Let's do A. So matrix A is 12, 2, 3, and 1. And matrix B is 6, 3, 2, 1, 4, 1. Okay? Now, let's see if we are allowed to multiply A times B. So first thing we're going to do, so is A times B defined? Okay? Can we do that? We're going to identify the dimensions. We have a 2 by 2, okay? And in B, we have a 2 by 3. So because these two numbers here are the same, okay, those two numbers are the same, the multiplication is allowed, okay? Now, let's see what happens if hold on one second. Okay, B work with me here, guys. Just give me a minute. I'm trying to do something like really technologically advanced here for me. Okay, so, all right. What we want to do now, isn't that cool, is let's see if B times A is allowed. Is that defined? Okay, well, if you look at your dimensions, we've got a 2 by 3 for B, but for A, we've only got a 2 by 2. So these two numbers here do not match. So multiplying B times A will not work. Okay? So that's how you can determine, again, whether your multiplication is allowed or not. Okay? So what we're going to do is, now that we know that we can multiply A times B, we're going to do it. Okay, so because these two numbers match, our solution matrix is a 2 by 3. 2 rows, 3 columns. Okay, all right. So let's start at the upper left and work our way, keeping in the same row, 1 column across each time. So row 1, column 1, right there, okay, will be 12 times 6 plus 2 times 1. And let's write all of these out, and then we'll go back and do the math on them, okay? Because I think that might just go a little quicker, so we don't break up the flow of this, okay? So then we would have 12 times 3 plus 2 times 4. And then we would have 12 times 2 plus 2 times 1. Okay, now we're going to move to row 2, and we'll stay in row 2 and then move our columns as needed. Okay, so lower left is where we're starting. 3 times 6 plus 1 times 1. And then we'll move to column 2, staying in row 2, okay? We would have 3 times 3 plus 1 times 4. Then we'll move to column 3, 3 times 2 plus 1 times 1. Now let's go back and we'll do the math and fill in our solution matrix. So 12 times 6 is 72, plus 2 is 74. Then 36 plus 8 is 44. 24 plus 2 is 26. 18 and 1. Okay. And then 9 and 4. And 6 and 1. Okay. So remember, the only way that you can determine whether or not the multiplication is allowed, so to speak, is by finding first the dimensions, the left to the right. Okay. The columns in the left matrix have to match the rows in the matrix on the right. That is the only way that you can determine whether the multiplication is defined. Okay? Now we get to example 4, okay, which is, it says, given matrix A, find the inverse, or the multiplicative identity matrix, which is a square matrix with 1 as each element on the main diagonal and 0 as every other. Okay, so find the multiplicative inverse is just going to be 1 on your main diagonal, so upper left to lower right, and then zeros everywhere else. Okay. Now, so the idea behind this is that you can multiply a matrix by an identity matrix and you'll get back the same matrix. That's the same idea that when you multiply anything by 1, you'll get back what you started with. That's what this whole thing is about, okay? So for example, we have matrix A, which is 3, -1, 8, and 12, okay? If we multiply that by the multiplicative identity matrix, which is 1s on the main diagonal and 0s elsewhere, when we do that multiplication, we will get back the same matrix A, okay? So let's test that. Again, practice makes perfect here. We have a 2 by 2 and a 2 by 2. So we know that the multiplication is defined and we are allowed to do it, okay? So that's multiplying A times our multiplicative inverse right there. We'll just call that I, okay? And because our multiplication is allowed, our solution matrix will also be a 2 by 2. So we'll start in row 1, column 1, right there, okay? So we have 3 times 1 plus -1 times 0. And then we'll move to column 2, 3 times 0 plus -1 times 1. And then we'll move to row 2 and column 1. Okay, and do the same thing. 8 times 1 plus 12 times 0. Okay, and then we'll move to column 2. 8 times 0 plus 12 times 1. So let's see what we get when we do this. 3 times 1 is, I'm going to change colors. Okay. 3 times 1 is 3, and that's probably a horrible color. 3 times 1 is 3 plus 0, which is 3 right there. And 0 times 3 is 0 plus -1, which is -1. Then we've got 8 times 1 plus 0 is 8. And then 0 plus 12 is 12. So you can see when you multiply in the multiplicative inverse identity, multiplicative inverse matrix, you get back the matrix that you started with. And again, the idea there is following the same logic as when you multiply any number by 1, you get back what you started with. The same rule applies here. Okay? Now we can, and eventually we will, go from writing a system of equations into a matrix equation. Okay? And then that's where we're going to stop today. But our equations are, from example 5, y equals 2x plus 5, x plus y minus z equals 8, and then 3y minus z equals 11, okay? So in our matrix, okay, we're going to do x, y, and z along the top, and then equations 1, 2, and 3 along the rows. However, we run into a problem here because we have x's and y's all mixed up in our first equation. So the idea is that we get x and y on one side of the x, y, and z on one side of the equal sign, and then the solutions on the other. Okay, so this is going to be the solution matrix right there. So the first equation, in order to get x and y on the same side, we have to rewrite it as negative 2x plus y equals 5, okay? And both the remaining equations, the variables are on one side, separated from the solution, okay? So I've got a negative 2, a positive 1, and I have no z's in that first equation. In the second equation, I have 1x, 1y, and a negative 1 under z. And then for the third equation, I've got 0 x's, 3 y's, negative 1z. And then my solutions, the constants to the right of the equal sign, go in order as well. Okay? And that's how you create an equation or a matrix from a system of equations. And what we're going to do is we're going to learn how to solve equations in 3 variables using matrix algebra, as opposed to using the equations themselves and eliminating a variable and then back subbing to find your values, okay? So matrix algebra can be simple, okay? And as long as we are very intentional on following our rules, it can remain as such, but it will take some practice, okay? All right, have fun with this.